Greetings and welcome to the RC Wall Vacuum channel. Today's video I'm going to delve back into RC electronics, and in particular I'm going to cover the fifth scale magneto kill switches. And in particular I'm going to review in detail a prototype I'm working on, and I'm trying to make nearly 100% fail-safe, and later in the video I'll show you why that's not going to be totally obtainable, but I'm going to get better than what's out there on the market right now. So in this video, I'm just going to cover initially. I'm going to cover a little background on the origins of this project, and cover some of the issues I've had with current kill switches out there. And then I'm going to go through and give a little demo on the bench with the on the Kraken here. And I got some waveforms. I got the scope. I'm going to hook it up to the magneto, show what comes off the magneto, and then I'm going to show what comes off the receiver that actually controls the kill switches. So a little background is I've only been in this hobby for 3-4 years, and in that very short time I've already had a couple of these kill switches fail. I won't say the name, but I can tell you when they fail, I want to actually take the kill switch and wrap it in a substance that has the same name as the kill switch and detonate it. And the manufacturer's name is not PETN, RDX, ANFO, or TNT, so there's a clue. I had one fail in the Lozy a couple years ago. I just pulled it out and scrapped it. I did take the cables off it because I figured someday I would need them. That proved to be true. I'm needing them now. And the current one is in the Vecta, and it's been a problem since I put the thing in. And it would run. It's fine when you first start off, but you run it for a little while, and all of a sudden it doesn't want to shut anything off. And so I'm going to show you right here what the problem was with that one. This is the kill switch I just pulled out of the Vecta. This thing, right from the time I installed it, has been kind of sketchy. It seemed like it was always okay when it was cold, but as soon as it warmed up, it would be a problem. So yeah, I pulled the thing apart. I wanted to see what was in there, and I wanted to retrieve the wires from my prototype. And as I'm doing it, I see the line that's the signal coming off the receiver was broken off the, in the box it was just, or the enclosure was just like sitting like that, so it was probably touching it, but the wire was basically broke, so that explained why it was intermittent. And normally it seemed like it was okay when it was cold, but once it would warm up, it would cease to work. So maybe it's just there was some expansion going on in that wire, pulling away from it when it would warm up. But anyhow, even a failure like that, even the failsafe I'm shooting for wouldn't be able to detect that because it's not going to know the receiver wire is broken off. And so the PIC's going to continue to hold that relay open. So that'd be another thing when I do the prototype. Definitely going to make sure that I have a system that allows them wires to be fully secured onto the board. And how they got that set up on there, that's questionable. It explains why it's broken off. I mean, these things just flat. I mean, obviously they snap into these plastic housings, but still, there ain't a lot holding that in place. So like I said, I'm trying to make this thing 100% fail-safe, and that little clip there shows you that, I mean, there's still going to be some issues where I'm going to come into problems with making a 100% fail-safe, but it can be done a lot better than what's being done right now. So as I was looking at this design and other designs out there, everything works with the normally open principle. And the problem with that is, for that to function, a whole series of events have to be correct. You got to have a power source. You got to have the switches got to be functioning. The actual kill switches got to be functioning right. The receivers got to be functioning right, etc., etc. So I'm going the other route, and I'm making a inherently closed setup, so that in theory and actually in practice, whether you lose your battery or your switch fails or your receiver locks up, this will shut the machine down. There are a couple routes for failures. One is if the microcontroller I'm going to be running this with was to seize up and hold the relay on. It's going to keep the contacts open because I'm using a normally closed read relay. I'll go more into that in a few minutes. Like I showed before, if a wire broke someplace, and there's other things. If the transmitter failed or something along them lines, there is a possibility of the read relay I'm using, even though they claim it can work at 20G environment and go to 50G shock, there always is a possibility that something could go wrong in there. It's real slim. So I'm trying to base this design on statistics. And statistically, things that are likely to fail in an RC vehicle are going to be your power supply or your switches feeding it or connectors. And when any of those things go wrong on these current designs, you're screwed. This thing's taken off. You ain't got no way of stopping it. Remind, if you lose a battery, the battery can come flying out when you do a rollover at full throttle. Well, it's gonna shut right off because no power, no function. So before I show the circuit, I got a couple of waveforms here. I'm going to tie it up to the magneto, and then I'm going to tie it up to the receiver and show what's what. And then after that, I'll go over the circuit, and then we'll hook it up on the Kraken and fire it up and see whether it shuts the thing off. Stay tuned. So I got the Vecta, I got this magneto tied over here to the digital storage scope. So let's set this thing up and give it some pulls and see what we get on there. So let's give it a couple pulls and see what we get. There we go. So that was obviously 5 revolutions. I'm giving it another shot. I'll just off the side of the screen. Yeah, so each pull I'm getting like 5 revolutions out of it. But I got the division set to, I believe, 50 volts of division. So I was getting almost 200 volts coming off that thing, off that magneto. That's obviously not on the spark plug side. So down on the bottom you can see some ripples. You see the main spikes, but you see a lot of ripples down there. That's a lot of the EMI noise that comes in and affects the semiconductors. So I'm going to change the volts per division on this and zoom so I can zoom in on the waveform, and we'll be able to show all the noise and crap that shows up at the bottom of the waveforms there. And let's give that a couple pulls. Yeah, you can see that. So you can see the spikes and you can see all the ugly crap that shows up on there. But those are the things that are going to cause false triggering on things. So the manufacturers do a pretty good job with these things of getting this stuff in and not having a false trigger off all that noise, especially the receiver manufacturers. So I got the receiver, which by the way is a Spectrum 6200 I believe, and I got a DX5, also Spectrum radio. So that right now is on aux 3, and I have this thing set up such that aux 3 is on the D button. On that one right there. And to activate it, you had to pull the switch up. To deactivate it, you push the switch down. So right now I just got the receiver set in an idle position, and I got the scope set for 200 microseconds and per division. So right now it's idle, coming off aux 3, and I'm assuming that's going to be the case, and I know that's the case with the throttle and steering circles. When they're sitting there with no control on, the centering position is a 1500 microsecond, which is equivalent to 1.5 milliseconds. I'm going to stick to the microseconds here just because that's how the scope's set up. But that is the centering off of the servos and off of the auxiliaries. So now when I go to activate the kill switch, pull that switch up, you can see the pulse changes, and to turn it on it goes down to 1100 microseconds, and it jumps back up to the idle of 1500 microseconds. Now to disable the kill switch, it goes down and that jumps up to 1900 microseconds. I've not yet put the scope on this particular receiver to see what comes off the servos, to control the servos. I'll probably do that later on. I don't know if I'm going to show it on this video or not. But I believe that's going to be closer to, the center will be 1500, but I think going to the far extreme is going to be 21 or 2200 microseconds, and back to the other direction is going to be around 800 to 900 microseconds. I'll do another video on that later on, but for now I'm just showing what comes off the auxiliary contacts of these things. And you can see that these, I got this set for, I believe it's a volt per division, so I got these things are coming off at 3.3 volts. I kind of figured that's what they were. Older servos were 5. These are down to 3.3. Although I think these are tolerant of 5 volts, but I'm not going to find out. Well, I'm back down here in the lab to give a little demo on the bench. I like using this proto station to develop stuff because I got access to an LCD and keypad and a bunch of other stuff, and all the components. So I'll give it a little demo here on the bench, and then I'm gonna give them the explanation of some of the parts that are getting used in this and why they're there, and then we'll move it up to the shop, and I'll tie it into the Kraken and give it a live fire test on the Kraken. But right now everything's all set up. I got the receiver engaged. It's in idle mode. This would be the mode when you first fire this thing up. I got two LEDs in here. Only one of this would be in the actual unit. This green one here is sitting across the LED, or sitting across the reed relay, and on the contacts. And it just shows the fact that this is green right now shows that your magneto would be shorted out. And the red here shows that your magneto shorted and you're not ready to run. So you can see you got the idle pulse, the 1500 microsecond pulse on the coming off the receiver. So I got the transmitter here, and this is the D button to engage it. So this would be in the field, you're getting ready to run it. You give it a kick up, and you see the pulse would have changed there. It goes right back to the idle pulse, and you got a green now showing you're ready to go. This LED went out, meaning this relay is now open. Your magneto is not shorted, and it would be ready to go. So you want to shut it down, then obviously you hit your button down, seeing the pulse there, and you got red, and now it's showing that the magneto is now shorted. So what I'll do here is simulate losing your battery power. I got this relay, or the Spectrum receiver tied into a LiPo and onto a little low-Z switch here. So I'm going to shut power off to the receiver, and that should, actually I'll tell you what, I'm going to take and we'll put it in green mode. So your engine's running. Now all of a sudden your mechanical power switch failed, or your receiver failed, or you lost your battery. There, it kicks it out. You see you got nothing off the receiver. Your relay contacts slam closed, shorted out your magneto, and you got a red indicator showing you failed. So then you get power back on, and you get the receiver signal back, but the micro keeps it locked out. You're still on a red. You still got a green down here showing your magneto is shorted. The only way to fire it back up is to actually push the activator button up to go. So that way, you don't have an issue that you got a sketchy switch here. You got a LiPo that's coming in and out. This thing is you're trying to shut the thing down, and it's taken off, and it runs and dies and runs and dies. So that'll eliminate that. I do have a lot more software development I got to do in the microcontroller. There's you got to look for a lot of different angles where there could be failures, different scenarios. So that'll have to be developed. But the core of it's ready to go. So I'm going to give a little explanation of the components, and then we'll go up to the shop and give it a live fire. So right there is the core of the parts that are going to be going in there. Start with the LED. I'm using an RGB LED, which is red, green, blue. I only need the red and green. The current versions I see out there only have the one color, and it's kind of confusing. So I want a situation where when it's red, you're not ready to go, and it's green, you're ready to go. So that's the point of that. There will be, obviously I have to have some current limiting resistors to that, so those will be in there. That's some of the small parts. This is going to be this is the regulator. It brings 7.2 or 7.4, whatever it is, down to 5 volts for the micro, and also it's a 5-volt coil on the relay. This little TL92 package, that's the N-channel MOSFET, and that'll be, the PIC's going to fire that, and that will in turn fire the relay. This little diode here, that's it's going to be in there as a flyback diode that sits across the coil of the coil of the relay. That's there to absorb when you collapse it. When you shut down a coil like that, there's a magnetic field around it. When that magnetic field collapses, let's see if I can get just the focus better. When that magnetic field collapses, it induces a current back into the coil, and the wires feeding it, and any component feeding it, but it's in reverse polarity. So this diode actually will take that and essentially circulates the power through that coil and loses it in the form of heat, keeps it from going back to destroying the MOSFET or anything else. Then this PIC microcontroller, it's a 12F1572. That's what I'm going to be using to run it. It's got an onboard oscillator, which just came with stay focused. got an onboard oscillator, so I don't need any external crystals or ceramic resonators and like that. So that saves a lot on fragile parts. And that will tie back to the receiver, and it reads all the PWMs coming off the receiver. And then the heart over here, heart of the operation is this read relay. When it comes to, like I was saying before, the difference between the normally open, normally closed. When it comes to normally open stuff, you got a lot of choices to pick from. There's the electromechanical, like the relays, but then in the semiconductor, there's MOSFETs, there's bipolar junction transistors, there's SCRs, triacs, probably a few other things I've forgotten that you can use on a normally open situation. But in this case, when I want to use a normally closed, so it defaults safely, your choices are much more limited. Electromechanical end, there's the relays stuff doesn't really change. There's plenty of picks to pick from with the relays with a normally closed. And usually they're a single pole dual throw, a dual pole dual throw. We have the normally open and normally closed. I didn't go with that in this situation. I got a dedicated normally closed relay because of smaller, just less components, less pins, and so that was the reason I went with the normally closed versus a single pole dual throw in this case. So, but when it comes to the semiconductor end of trying to deal with a normally closed, your choices are very limited. You basically have only depletion mode field effect transistors. The MOSFETs, they have both depletion and enhancement. That is an enhancement. Of course, you got to gate it. You got to gate it to make it conduct and turn on. Where depletion, it's on all the time, and you got to gate it to shut it off. The problem is the MOSFET depletions are not super rugged. The other option is in the field effect transistors is the JFETs, which are only available in depletion. They're a little more rugged. I may look at going into a JFET in the future on this, depending on how the relay system works. But I like this relay setup because it can go up to 50 G shock. It's a magnetically held, normally closed, and then obviously the fire to break to split the contacts on it, break that magnetic field. But I like that. I think that's just it's a good. It'll hold up to the shock involved in this. There's very little power consumption on it. I think it's a win-win situation for this particular application. But I may look at the JFET in the future. But for now, I'm sticking with this. And like I said, there's a couple of resistors for the relay or the LED. I'm not putting any kind of snubber circuit on the contacts of the relay off the magneto because the way it's normally you'd want to have on a relay when you're switching onto it, you got a normally open switch and a load in, you want to have some kind of snubber on there to suppress the arc that's going to build when it breaks the load. In this case, I don't think that's going to be an issue because you're not really breaking a load. You're basically when it's opening, there is no load on it, so I don't think this should be a problem. So I will be able to get this down in a real small board. I may switch to some surface mount components, but for what I'm going to do once I got some more development to do on the proto station here on the bench, develop some of the software, and I'm going to take these through hole components, pack them on a real small board, 3D print a little housing, and piggyback it onto something in Kraken and give it some tests, and then depending how it works, I'm going to take in I'll design a surface mount board and probably try to put some of the stuff on a surface mount. So anyhow, enough babble. I'm going to take and go up and hook this thing up to the Kraken, and we'll give it a live fire on the Kraken. Stick around. So I have the patient wired in, and we'll give this a test fire and see if we can get this thing to go. Alright, it works. Got a red light over there, and it shut down. So you can see it worked well. I got some more software I got developed on, stuff like that. And then I was a little concerned with this setup. I might have some EMI issues and causing glitching on this thing, because I don't have a lot of EMI protection on it at the moment. But it worked fine. I didn't have any issues with it. So like I said, I got more software to deal with. And then with the EMI, I got to take in, I didn't mention previous, but also on the final version, there'll be a bunch of decoupling capacitors put on there, especially on a microcontroller to to deal with EMI. That's why when you get these kill switches, they got these ferrite chokes on there. Those are meant to suppress EMI or high frequency EMI mostly. I put some extras on my extension line over here on the coil. I wasn't too concerned about the receiver. So if you're interested in one of these this kind of switch setup for your own vehicles, check back. I'll be updating this as I work on this along with a million other projects I got going on. But this one I kind of want to push because I want to start using this in my own vehicles because to me failsafe means failsafe, not well maybe it's safe, but I really don't feel like sending one of these things into someone's leg or sending it off a cliff somewhere if I can avoid it. So anyhow, I hope this is informational for you and maybe a little entertaining. But thanks for watching. Check back. I'll be giving updates.